Okay, we're going to kick off electricity with a short section on the flow of charge. Now we've managed to break electricity down into 5 nice short little bites which you can listen to very quickly, so I'm going to keep going. All electricity, which we call current, is the flow of charge. It's the movement of charged particles from one point to another. Now I'm going to confine myself in this section to look at the flow of charge in a solid, and that's a metal, and that's electrons. Of course, because at the time when electricity was being written, when all the laws and the ideas were coming out, we didn't know that there was such a thing as an electron. We don't actually have it the right way round. We believe that electrons now flow from positive to negative, and that's what causes current. But at the time, conventional current was thought to flow in the other direction. It's very unfortunate. Electrons flow towards, obviously, the positive because they're negatively charged, but we consider mathematically charge flowing in the other direction, and no one's really ever got round to changing this. It's a little unnecessary, so maybe why do we bother? Now we come on to the most important formula, which is not in the log tables. Unfortunately, this formula, which is sometimes called the quit formula, for reasons I'll explain in just a moment, you get Q equals IT, which if U is your equals, then you can call it quits, you know? Anyway, that's another way of writing the same formula. This expresses the idea that current electricity is actually charge per time, or the rate of flow of charge. Now, you do really have to remember this formula if you're going to do an electrical question. If you're not, no. Here's some of the electrical questions you might be asked on such a thing, where you have given the current and the time the current is flowing and asked how much charge is flowing. This is a fairly common question you can be given. You can also, of course, be given the charge and the time and be asked to work out the current. These very simple calculations. It also can occur when you're given the charge and an electron and the flow of the electrons and asked either how many electrons are flowing or what the current is conversely. But this is just Q equals IT formula. You're afraid you will have to remember it if you're considering electricity as one of your subjects. Now, some of the basic ideas in electricity are incredibly simple. This one is an absolute breeze. If you put in an extra battery, you get more light. So more current is flowing, more electrons being pushed around the circuit by the batteries. However, if you put in more resistance, you put in an extra bulb down there at the bottom right, you get less light because the current is decreased, because it finds it harder to move around the circuit. Now, if we hold on to these basic ideas, everything else is simple. We mustn't move away from the idea that the flow of current is about how easy it is for the electrons to move. If we can keep that in our head, the rest is really easy. So, if we keep that idea, let's look at what it means for a circuit which is what we call series. Everything is connected to each other, one after another. The caterpillar of the electrical world. Around the current goes around the circuit, and everywhere you look at it, you find it to be exactly the same. Of course not, because if it was flowing more one place than another, it would build up, it would flood, and that's impossible, only in short circuits and breakages. If the circuit is working healthily, then the current must flow in the same amount each time. And the amount it flowing must be how difficult it gets to the hardest point on the circuit. However, if you introduce another branch to the circuit, the current can split and go a different way. In that case, the current can flow in different parts or different amounts in different branches of the circuit. So, in branch number 1, it's flowing differently to branch number 2, unless, as I've indicated, the two bulbs are the same, and then it's simply going to split in two because it's just as easy to go down one branch as the other. If you introduce a third branch, you simply split it into 3. Here I've just tried to put some numerical values on it. So the entire circuit has 6 amps flowing in it. So 6 amps is coming out and going back to the battery. So at each of the branches, we have split it into 3. So 2 amps flows in each of the branches. But once we return back up here again, it's going back to 6 amps. This greatly assists us when we're trying to do calculations, these simple ideas that we have to understand. Here we have a battery of 2 cells which are providing 6 volts. That's the EMF of the circuit, the electromotive force, the total voltage drop between the beginning and the end. So this branch closest this battery may be at 6 volts and this one at 0 volts. Because there's a direct connection here, this section is also at 6 volts. But because the fall across that lamp, that signal lamp, is 2 volts as indicated there, this must be 4 volts. There's 2 more voltage drop over the next lamp. And when we get to the far branch, we've gone down to 0. So each lamp has a voltage drop of 2 volts. That's called the potential difference, the potential difference. And it's also, as you can see, why we measure the voltage across the instrument. We're looking at the drop of voltage. If you take 2 of these bulbs, of course, then if you have 6 volts there and 2 volts here as in the previous, now the drop is 4 volts, which is what you measure on the voltmeter. However, in a parallel circuit, the voltage drop is the same at all times as the EMF in each branch, because essentially each branch is connected directly to the battery. So wherever you go in the circuit, you have 4 volts. Each of the voltmeters will indicate 4 volts, because they're all connected directly across the battery. So, summary. Current is the same at any point in a circuit, but the voltage splits up over each component. Whereas in a parallel circuit, the current splits up down each strand or arm or branch, and the voltage is the same across each strand. Now, there you go. Throw you straight into the deep end. Let's try and pick off some of the low-hanging fruit when it comes to this section. What are the different voltages going to be and the different currents? Well, the easiest one is this one. Now, I want you to pause and try and fill in all of the missing and then see if you agree with me. Okay, I hope you're back now. This is 3 amps. Because the both on the 3 amp on this side must be the 3 amp on this side. Must be the same everywhere in the circuit. The next easiest one is this one, because it's connected directly across the battery. The only load, the only drop in voltage in the entire branch, if you follow, I'm going to try a different colour now. Yes, let's try green. If I go round this way with my current, the only drop is in this signal bulb. So that must be 6 volts, the same as the battery. Okay, now that makes V2 and V3 also very interesting. As the bulbs are the same, what do you think their voltage will be? Yes, you got it? 3 volts each. That's meant to be a 3. Hey, 3 volts each, because they're the same component. If they weren't the same size in resistance, then you wouldn't have 3 volts each. But you have because they are. The last one, the current, is a little bit more difficult. It is twice as easy for the current to pass upon the upper branch as the lower. As there's 3 amps in total, then it'd be easier just to think of this as simply 2 amps and 1 amp. The majority of the current flowing down the easier branch. But they do follow in the ratio of their resistances. That's a little bit more mathsy, a little bit more ratio, but still I think easy enough to see. So having looked at the differences between series and parallel circuits, I now have to tell you how you'd be an idiot to use a series circuit. Series circuits are really, really silly. Now there are 3 reasons. I have written 2 of them down here, but there is always reason 0. Reason 0 is known as Christmas light syndrome. It's a cause of so many divorces. I really worry about it in the future, because men trying to fix Christmas lights, women trying to fix Christmas lights, cause arguments with their partners, which often end in divorce. It's a terrible, terrible toll on the community. And what we have to do is eliminate it by bringing in parallel circuits everywhere. So point one, an advantage of a parallel circuit is you can add as many appliances as you like plugging in at home, like turning on your lights, turning on your lights, and all the lights come on instead of them going dimmer the more you turn on. Here, if we add another bulb there, it's just as bright. Yes, the battery may wear out quicker because it's drawing more current, but there's no change in brightness, current, or anything else in this circuit. By the same token, point number 2, if any of them break, or if, and this is more likely, we want to turn one of them off because we're going to bed, well then the others do not necessarily go off. And in fact, we can turn all of them off and not have any problem with the circuit. So, extra appliances can be added or subtracted, things can break or be turned off without affecting the other bulbs in the circuit. So these are the advantage of parallel circuits. Moving into a much more mathematical treatment of this, we have to look at resistance. Resistance is difficult to put as a physical quantity. It's a ratio, really, a mathematical construct we use. First used by this guy, George Simon Ohm. Now, George Ohm was German. That's not why he's frowning. I think he's frowning because of the type of picture they used to take at this time. It's called a daguerreotype. And he had to stand there for about 20 minutes looking like that. So a smile was probably out of the question. He could have done something with his hair. Anyway, resistance, hair. Who am I talking about here? Resistance is voltage over current. It's a simple ratio. You simply divide the voltage at a point. I mean a load here. I mean a resistor, a lamp, a coil, something that's using the current. That's called a load, something that's actually doing something. Voltage divided by current gives us our resistance. Here's a very easy example. Suppose in this series circuit there's 2 amps flowing, which means there's 2 amps flowing all the way around. And in that particular bulb, there's a drop of 10 volts, a potential difference between the 2 sides of the bulb of 10 volts. That means 10 divided by 2, that bulb must have a resistance of 5 ohms. And whatever circuit we put it in, as long as we didn't burn it out, as long as we didn't heat it up too much, because bulbs change their resistance when they heat up, we can have 5 ohms. Now, if they're all 5 ohms, they add up to 15 ohms. And then we can find out that naturally this is 30, that the bulb, each bulb has a drop of 10, meaning the EMF in the circuit is 30 volts. I'm going to let you do these. These are kind of fun. I think they're easy enough, and you just have to work your way through them. Now, the experiment we have to learn how to do is this one. Now, I've replaced the battery with a plus minus 6 volts supply, meaning a DC supply. This is perfectly legitimate. You can do this as a DC supply. It means it's plugged into a power pack or something like that. Now, the advantage of this is you don't have to remember which way around the battery goes and get it wrong. Not so important in this experiment, but very, very important when we're doing semiconductors. So what else do we need in the circuit besides a power supply? We need a variable resistor, which is this device here. That's a variable resistor, a potentiometer or a rheostat. A rheostat, you slide the slider to adjust the resistance, which is something you can be asked. How do you vary resistance? They don't want you to know you vary the variable resistor. That's not really an answer. They want to hear that you've slide the slide on the rheostat. Easier to write than to say. Then, of course, because you're trying to look at the difference between current and voltage, you're examining resistance, you need something to measure the current, which is called an ammeter, and something to measure the volt, which is a voltmeter. And then this is the sample. In this case, we're looking at a metal. The most common metal to be used in this experiment is nichrome, because it has a fairly high resistance for its length, despite being a metal, and doesn't heat up that much, even though being thin. So it's a nice one to do the experiment on. Now, as well as putting the nichrome here, you can put the bulb where the nichrome is. You can put a liquid like copper sulfate with copper electrodes to look at the flow in an electrolyte. And you can also put a diode, either placing forwards or reverse, depending on you're looking at forward or reverse bias. So, as I said, metal conductor, filament bulb, copper sulfate solution with copper electrodes, semiconductor diode. And what you get from these experiments are these. These are called characteristic curves. Number 1 on the left is for the metal. It obeys Ohm's law because on both sides, it's a straight line running through the origin. And in order for the two to be proportional, I to be proportional to V, which is essentially what Ohm's law is saying, that the two are proportional to each other, there has to be a straight line through the origin. Now, a bulb does not obey Ohm's law. That's the one in the middle. The bulb, as you can see, is not a straight line. It may go through the origin, it may not, but it's not a straight line, so it is not ohmic. It doesn't obey Ohm's law. Neither does a diode. Although there is a certain numbers of diodes which are a linear relationship between current and voltage, for a start, they only flow in one direction, which stops them being obeying Ohm's law, but also they never ever start from zero. That's not an accidental drawing. They are slightly offset. That's a certain amount of push or voltage that's needed before the current starts to flow. It's called the junction voltage, and it's about 0.6 of a volt. But because of that, definitely doesn't obey Ohm's law. So here is your question. No tricks here. Very nice little question 4. As you know, I'm a big fan of question 4. The only one I'd be aware of is a little bit cautious of is Joule's law, but even then, there are some good marks to be made on most of them. So, crack on. Good luck with that.